Hello everyone, we are Summit Builders, Illinois' leading general contracting firm. Our key team members are Suresh, Anam, Harshal, Kanchan, Robin, and Morris. We are a team of experienced project engineers, project managers, and cost estimators. We specialize in high quality educational buildings with a keen eye for energy efficiency, sustainability, and high end finishes. It is an honor to be working on a project for this prestigious U of I's ECE building. The ECE building is going to be a space for high-tech learning and collaboration. The building is about 230,000 square feet located on 306 North Wright Street of Urbana. The project duration is about 4 years and the budget is about $95 million. The user is going to be the Department of Electrical and Computer Engineering. The ECE building site is located in one of the most central location of the university town, that is North Court, with Beckman Institute to its north and Nanotechnology Lab building to its south. The site has its main entrance from the North Wright Street, and the east side of the site has a huge open lawn area, and it has a pedestrian street on all four sides.
The main purpose of this project is to provide clear instructions to the construction team. It tells them what needs to be built, how to build it, and in what order to do so. It includes details about the material and equipment that will be used, the design of the structure, and the timeline for when each of the parts of this project should be completed. The objective of this project is to ensure that the project is completed successfully. Successful completion of this project means that the structure should be built as designed, within the planned timeline and within the budget that was set for it. The plan also aims to ensure the safety of the workers during the construction and that the final structure will also be safe to use.
During construction and development projects, it is indeed important to mark a side boundary, which is typically larger than the property boundary. The red light in the picture indicates the side boundary, which is encircling 4 pedestrian walking sides around the building and almost half of the ground behind the building. Signages plays an important role in information and safety. There are 3 types of signages being used on this site for public. Those are sidewalk closed, site under construction, and informatory signs.
The major impact of construction would be for pedestrians. The area is actively used by pedestrian traffic, which will get affected due to closing of sidewalk in the west of the site. Taking away few portion on the construction boundary in the east side of the site in the quad is also going to restrict the pedestrian traffic. The red lines in the left diagram shows the regular pedestrian movement before the construction, and the blue area marked in the right diagram will be the closed sidewalk areas when the construction begins. The pedestrian will be diverted through crossings as marked by red arrow. The north pedestrian walkway is accessible while the south walkway is blocked and included as a part of site boundary for construction. There will not be much impact on vehicular movement as there is generous number of gates to the site, which will not impact the regular vehicle movement due to trucks and site work. A stop or a construction warning sign can be implemented to control the speed of vehicles, consequently helping with the safety of public.
To efficiently manage operations during construction, we'll set up temporary field offices and storage areas. 4 gates will be installed, 2 for vehicles and 2 for personnel. Initially, field offices will be located on the south side to oversee excavation and foundation work. Once the structure is up, offices can be relocated inside. The staging location for materials will be on the east side for easy truck access. This area will serve as a temporary storage zone during deliveries and material handling. We have created different areas for offices, storage, and site access to ensure that operations are well organized during this important initial phase of construction. To smoothly transport materials on and off site, we've designated specific loading and unloading zones near the staging areas. These temporary locations will allow deliveries to be efficiently received and routed where needed. The open area in front of the building is well suited for bulk materials like concrete, which won't be stored long term. By planning in advance where trucks can pull up to unload, we can avoid bottlenecks and keep the flow of deliveries on schedule.
The possible truck route has been tracked from a potential supplier, that's the prayer material supplier. In the figure, the truck can move from the West Springfield Avenue to the South County Fair Drive and then onto the West University Avenue and the South Wright Street before entering the site. The University Avenue towards the north of the site can be considered for all the potential truck access, as this road has no overpass of 11 feet 10 inches which can be observed in the West Springfield Avenue towards the south.
For the additional site preparations, besides the standard ones, we would also need a permit from the university because our site boundaries cross the North Quad. We would also need a fence for security and privacy, given that we are near a main street. The type of fence that we're going to use is seen as in the picture. We would also probably need to make the southwest man gate as an additional emergency gate for vehicles.
Identifying utilities is one of the most important activities before performing excavation. We call JULI to identify utilities. JULI stands for Joint Utility Locating Information for Excavators. JULI is a not-for-profit corporation that provides contractors, excavators, homeowners and others who may be disturbing the earth with a free service phone number to call for the locating and marking of underground utility facilities. JULI uses the following color coding to locate specific utilities: red for electricity, yellow for gas and oil lines, blue for water, orange for communication, and so on. We have also listed the owners and their contacts for each utility, and we need to contact them before disturbing any of these lines. As you can see in this slide, we have also indicated the utility locations on the site demo drawings.
Site clearing is a crucial first phase in the construction project. We are assuming obstacles and vegetations on the site which need to be cleared off, and the equipment used for it are excavator, loader and dump truck.
Site demolition is one of the important steps before you start the construction process. When the site was investigated based on historic data and existing site conditions, it was found that no demolition was required before the starting of construction, except the clearing of few peripheral trees and vegetations.
In the excavation and site work for the University of Illinois Electrical and Computer Engineering Building, various specialized equipments are crucial for efficiency, safety, and precision. These equipments are as follows. The excavators would be used for digging and earth removal. The bulldozers are vital for terrain leveling and shaping. The backhoes would provide precise digging and trenching capabilities. The loaders would be used to move the materials on the site. The dump trucks would be essential for soil and debris transport. The surveying tools would provide total station and GPS for accurate measurements. Lastly, the safety gears would provide equipment to ensure a safe working environment.
Phasing in excavation is an important step for efficient and effective construction flow. Building construction is divided in two areas, Area A and Area B, as the north and south plus central wings respectively. The order of excavation is determined based on accessibility for excavator and trucks and manpower. The The efficient zone to start the excavation is from the northwest corner of the building area A, and consequently following the building footprint to enter in area B. The last point of excavation shall be the northwest corner of the south wing, that is the northwest corner of area B. The excavator and truck positions are marked in the following diagrams along with the direction and area of excavation. For increasing productivity rate and reducing the time of excavation cycle, the excavation is divided into two phases, Phase 1 and Phase 2. Phase 1 excavation depth is 10 feet, followed by Phase 2, which is 20 feet of excavation depth. For this purpose, along the timeline of start of Area B excavation, in Phase 1, a slope has to be constructed in order to start the excavation of Area A in Phase 2. The following timeline figure shows the scheduling of these phases with respect to their areas. Consequently, when the Area A excavation of 20 feet is completed, the foundation excavation phase of Area A can begin, while Area B Phase 2 excavation is still undergo. Based on the calculation of approximate volume and the workflow as assumed based on the timeline, number of excavators that would be operational at a time would be 2.
Now that excavation is complete, it's time to remove the heavy equipment used in this critical early phase. First, operators will clean and inspect each machine to ensure it's in good condition for transport. Excavators, dozers, backhoes, and other large vehicles will need to be safely loaded onto trucks. Once the site area is cleared of debris, it will be left in a clean state, ready for the next stage of foundation work. Properly demobilizing excavation gear is important for construction to smoothly transition and keep the job site safe and organized. The foundation system has different types of footings, such as square, combined, and continuous. These footings are designed to accommodate various soil conditions and structural loads. Footings will range in size from 5 feet to over 15 feet and depths of 18 to 44 inches. With rebar reinforcement, grade beams, and a 5 to 8 inch thick slab on grade are also part of the design.
During this phase, in addition to equipment from the site building and excavation phase, we employ tools to fortify the foundation. These include the trench boxes that would be used for ensuring worker safety, the formwork that would be used for crafting molds for concrete foundation using wood or steel forms, the concrete finishing tools that would be used for achieving a polished surface. The concrete mixtures would be used for mixing and transporting concrete for the foundation. In addition to that, the concrete pumps would effectively be helpful in placing concrete in large areas. Lastly, the vibrators would be essential for consolidating and compacting freshly poured concrete, ensuring its strength.
Foundation phasing will take place based on the area divisions. Let's call the foundation of Area A as Phase A and foundation of Area B as Phase B. The location and accessibility of equipments will differ based on phases. On the start of Phase A, the Area B excavation would still be undergoing. Hence, the central zone between the buildings would be under the use for excavation, dumping, and hauling. Hence, in Phase A, the Gate 1 will be utilized for access of concrete pump, and the red hatched area along the north periphery of the site will be used as a potential location for concrete pump and mixer truck. For Phase A, the steel rebar staging area would be the northeast corner of the site, marked in yellow. When moving to Phase B, the central portion of the site shall be utilized for concrete mixer and pump trucks, and the steel rebar staging area will be moved more to the south along the east boundary, as marked in purple color. For this phase, Gate 2 will be used as the primary gate for truck movements.
Here is the calculations we performed to measure quantity of concrete required for foundations. We first identified spread footings, which include square footings and combined footings. As shown in the details, we also identified continuous walls, continuous footings and slab on grade. The total concrete we would need is about 3,800 CY. Based on the calculations, we came to a conclusion that we would require about 380 concrete mixers of 10 CY capacity, and the concrete will be poured component by component phase wise. That is, first we'll be pouring the foundations and slab on grade and walls for phase A, and then for the phase 2.
After completing the foundation construction, the large excavators and bulldozers will be loaded onto transport trucks. Backhoes, loaders, and dump trucks previously used for moving materials will also be loaded onto trucks. Cranes will lift and secure heavy trench boxes and concrete forms for the next project. Smaller tools will be manually packed, and the site will be readied for the next phase of work. Steel framing forms the main structure by supporting beams, columns, girders, and trusses that span between the foundation and floors. The structural plans show the layout and dimensions of these elements to transfer loads down through the building. Coordination with other building systems is also vital, as equipment and openings may impact the steel framework.
After performing detailed superstructure analysis and our expertise, we have listed the following equipment requirements. Lattice boom crawler crane to lift heavy weights such as columns, truck mounted telescopic cranes because it can maneuver around the site easily and to lift lighter weights, concrete pumper truck to pour concrete for floorings, concrete trucks equipped with rotating drum mixers which continuously churn and mix concrete to ensure concrete remains in a workable state, mast climbing platform for a safe and controllable platform for workers to reach to the elevated heights, concrete forms for shaping and supporting the concrete during pouring, safety net for the safety of the workers on higher levels.
The superstructure is divided into 3 phases. The first phase is structural steel frame. Here we are using 2 types of cranes, lattice boom and telescopic crawler. The lattice boom crane will be used for erection of the steel columns, and the telescopic crawler will be used for erection of beams, girders and metal decks. Phase 2 is metal decking and concrete pouring for flooring. This includes laying out, securing and creating openings for decking and preparing, pouring, vibrating and compaction with finishing and curing of concrete. Phase 3 is steel structure, erection and concrete pouring for roofing. This includes assembly of cranes, column installation, beam installation, truss installation, pressing and bolting, and formwork reinforcement and concrete pouring process.
The superstructure demobilization would begin with first looking at all the safety precautions and site evaluations, disconnecting the utilities such as gas, water and electricity. The formwork would be removed by using cranes or hands based on the necessity of the situation. Then we would address the local laws and regulations for environmental considerations, finally inspecting the site from the plans. The different equipments such as the cranes would be first dismantled from the boom and the counterweight driven out and secured from the site. Then moving forward to concrete finishing tools, we would simply pick the tools by our hands, pack them and keep it in a secured position for future use. Similar to the concrete finishing tools, the formwork and the mast climbing platform would be stored and followed with the necessary systematic process, kept in a secured place for future use. Lastly, The scissor lifts would be lowered, disconnecting the power and driven from the site in a secured way.
Mechanical systems are essential components in modern building for maintaining air quality, inside temperature, energy efficiency and safety. We are using three mechanical systems in our project. Those are heating system, ventilation system and temperature control system. The heating system used in the building is known as hydronic radiant heating system. This system uses warm water through network of pipe installed beneath the floor for heating. This system has many mechanical components such as trench, wall box, plank of panel, utility support, chilled water branch, etc. The ventilation system used in the building is known as HVAC system, where HVAC stands for heating, ventilation and air conditioning. This system uses hot and cold water for heating and cooling respectively. Some of the main components and connections which are used in this system are trench air box, round duct tape connection, fire and smoke dumper, goosenecks, fume hood fans, etc. Temperature control system installed in building uses water-based system to regulate indoor temperature effectively. These systems utilize water to either heat or cool indoor spaces, ensuring comfort and energy efficiency. There are several components used in this building such as chilled water system, cooling water loop, vacuum pump, clean water system, fan coil, domestic CIRC pump, etc.
Coordinating the mechanical systems in a complex building like this is crucial. We need to plan chase routes for ventilation ductwork that don't interfere with other trades. The layout of heating pipes and air ducts also requires alignment with structural elements to allow access and space. Placement of control panels, sensors, and wiring for temperature regulation needs consideration for accessibility and future access to penetrations. The HVAC installation will be phased floor by floor starting from the lowest level. Ductwork and equipment will be installed level by level to allow crews to work efficiently. Next, the north wing will have its equipment installed, followed by the south wing. The tasks will be organized according to the trade, starting with the installation of ductwork, followed by fitting and insulating. It's important to run electrical wiring before mechanical work is finished. The air handling unit, fan and controls will be installed first to allow for testing before occupancy. Startup and commissioning will occur per floor and zone after each area's installation is complete, from the first to fifth floors and finally the penthouse.
Foundation to any successful project is efficient and effective electrical coordination, which ensures a working, safe, energy-efficient environment, and that our clients' needs are met. ECEB has a thorough network of electrical systems which has to be efficiently handled and coordinated to achieve the output as proposed. And as a contractor who is in charge of electrical coordination in this building, we make sure that electrical systems are designed and installed efficiently. Distribution of electric power, lighting, safety precautions, and adherence to construction requirements are all included in this. We are committed to maintaining the highest standards of quality, compliance, and sustainability, contributing to the advancement of cutting-edge technology and innovation in the field of electrical engineering and beyond. Our goal is to facilitate the seamless integration of power, lighting, and advanced technologies, fostering an environment that empowers both student and faculty to excel their pursuits. The systems that were identified were main electrical systems and backup electrical systems. While doing the floor-wise investigation of design, several electrical systems were identified on each level. For example, site level has electric manhole, duct bank, pole bases, plaza lighting in generator pad. The basement level has lighting, electric room. The upper floors are mostly lighting, in which the fourth floor has an elevator machine room. Several kinds of lighting fixtures were also taken into consideration, taking into account the phasing of fixtures with respect to exterior and interior construction phases. Few electrical installation notes are listed here for your reference. More light to the components. Some of the main components as mentioned and marked are electrical manhole, duct bank, pole base, lighting, circuit breaker, transformer, distribution panel, magnetic starters, switch gears, conduits, cable, junction boxes, and some of the backup components are generator and solar panels. In the following slide, more details for electrical component is documented and planned in the form of figures. Looking into the distribution components on each level, an electric room suffices the requirement. The electric room is situated at the corner of the building and there are two in one wing. The electrical room has a panel, a distribution panel, and a busway. All these lead the conduits to the respective power output. Here were the pre-planning and investigatory slides for data required for the next step of planning. The upcoming portion for the electrical details will be covered by my colleague Harshit.
Phasing the systems during different stages of construction would be a critical step to ensure smooth functioning of the electrical systems. In phase 3, that is during the excavation process, it's important that we would dug the duct banks and the generator pads along with the excavation. In phase 4, that is during the foundation and the substructures, we would emphasize on developing the temporary electrical lines for construction needs. Some of the conduits would be embedded in the floor slab of the basement. In the phase 5, that is during the superstructure, the conduits and the electrical connecting lines would be embedded and casted in the floor slab. Lastly, moving forward into the exterior and interior finishes, which is still under investigation, we would look to have the facade lights for walls, interior work like switchboards, electrical sockets and fixtures would be completed in this phase. Following equipments would be necessary during different phases of construction for smooth electrical coordination. The lattice boom cranes would be used for heavy equipments for lifting heavy loads. The concrete pump and the mixer truck would be essential for the generator pads and duct bank construction, facilitating concrete placement. Additionally, a scissor lift would be used to transport vertical elements such as conduits and fixtures to higher areas within the construction site. Smaller equipments would be required for electrical fittings. These would include equipments which help to hold and pull the wires together, such as the T-stripper and the cable puller. Further, drilling machines would be needed to drill holes in the wall. The long nose piler would help to grip, bend and cut the wire in tight spaces. The wire reel caddy would help to transport and dispense wire reels. The fish tape would help to thread and pull electrical wires through the conduits and the wall. Lastly, we would require different voltage testers, multimeters and circuit finders to detect, diagnose and locate and identify electrical circuits in the building.